Great. Good morning. Welcome, everyone. On behalf of the Southern Alliance for Clean Energy, I would like to thank you for joining today's webinar about how climate change is impacting hurricanes. And of course, we've put together a briefing today for both members of the press and also our allies. I'm Susan Glickman. I'm the Florida Director of Southern Alliance for Clean Energy, and my colleague Carnival and Colin are helping with the slides and so forth. So next slide. For those of you not familiar with Southern Alliance for Clean Energy, we're a regional membership organization. We promote responsible energy choices to ensure clean, safe, and healthy communities throughout the Southeast. And we would like to acknowledge our members on this call and encourage those of you who are not members to please join us. There are different ways that you can get involved, become a member. So go on to our website, www.cleanenergy.org. So now I'd like to take a brief moment just to review the basic functions of the Zoom platform. It's on the bottom of your screen. All attendees are muted throughout the presentation just to make sure we have good sound quality. But if you're having any trouble hearing or seeing the slides, just click on that chat button along the bottom and then tell us what your problem is and we can help you troubleshoot. So we've also saved time at the end of the presentation to answer questions and have discussion. So when you have a question, just click on that Q&A button along the bottom of the screen and we'll work to get to as many questions as we possibly can at the end. And lastly, we are recording this webinar and it's going to be posted on our YouTube channel. So you'll be welcome to share that with others after you've sort of listened to it, and you might think of people that would be interested as well. So joining us today is Dr. Timothy Hall and Dr. Jennifer Francis. Timothy Hall is a senior research scientist at NASA's Goddard Institute for Space Studies in New York City, and he's an adjunct professor of applied physics at Columbia University. His research addresses extreme weather hazard and its variations with climate. He has a particular focus on tropical cyclones, and he's got over 60 peer-reviewed publications and was a lead author on the 4th National Climate Assessments, a 2017 Climate Science Special Report. As part of his research, Dr. Hall has developed the North Atlantic Stochastic Hurricane Model, so that's a mouthful, which he uses to address questions such as the climate evolution of hurricane landfall rates, as well as assisting private sector stakeholders in hurricane risk analysis. Dr. Hall has also built models for tropical cyclones and other ocean basins and winter storms over North America. So in addition to his NASA position, Dr. Hall serves as a meteorologist for the Florida Hurricane Catastrophe Fund and has worked as a consultant with several modeling companies. He holds a PhD in physics from Cornell University. So we are very, very happy to have you. And let me also introduce Dr. Jennifer Francis, and Dr. Hall will start with his presentation first, and then we'll have Dr. Francis go after that. Dr. Jennifer Francis is a senior scientist at Woods Hole Research Center. She's an atmospheric scientist, and she's nationally recognized expert on Arctic climate changes and the effects of rapid Arctic warming on weather patterns in mid-latitudes. Her research is focused specifically on a connection between the rapidly warming Arctic and a weakened jet stream. She is regularly quoted in major media outlets, including the New York Times and the Washington Post. And in 2019, she testified to the U.S. House of Representatives Science Committee on Climate Change and its connection to extreme weather. So with that, I turn it over to you, Dr. Hall.
Thank you, Susan. Thanks to Susan Glickman and the Southern Alliance for Clean Energy for inviting me here. It's a pleasure to be here. I'm just sharing my screen now. And I hope you all can see my screen.
Tim, it's working for me. So again, if anyone has any problems, just shoot us a note in the chat.
Okay, excellent. So thanks for the introduction, Susan. And my name is Tim Hall. I work for NASA at a laboratory in New York City on the Columbia campus. doing work on our lab's mission is climate change research, and my particular focus is extreme weather and hurricanes. And I'm going to talk about sort of a top level view of the sort of state of the knowledge of hurricanes and climate. But I'd be remiss to not review the last couple of seasons. The 2017 and 2018 hurricane seasons, as just about every one of you will know, were highly active seasons with record-setting flooding, Harvey and Houston, Florence in North Carolina, thousands of fatalities from Maria in Puerto Rico, and also included only the fourth U.S. Category 5 landfall, Hurricane Michael in 2018 on the Florida Panhandle. What about the 2019 season, which has just started a couple of days ago officially? Well, the seasonal forecast for the season is quote-unquote average. But I want to make the point that seasonal forecasting is very hard. In fact, it's harder than weather forecasting. It's actually even harder than decadal long-term climate projection. So average really means we don't have any basis to say that it's going to be high or low. And I will point out that the 2018 forecast, a month before the season started last year, was also average, and 2018 spawned Florence and Michael. But I'm not here to talk about seasonal forecasting. The hurricane climate analysis is based on a long-term view and a physical understanding, not just a few active seasons. So I want to talk about some of the long-term climate impacts on hurricane, and I'd like to organize this in the following way: a list of the impacts of a changing climate on hurricanes ranked from what we know best of all and what we know with less certainty. So the top being what we know virtually for sure, and as we move down with more and more uncertainty. So the first thing, number one, is actually not even a climate change issue. It's simply that there's more population and infrastructure in harm's way. So even if the hurricane hazard wasn't changing, we have more vulnerability. The second has to do with sea level rise, which is just about the most robust projection of a changing climate. So even if hurricane statistics weren't changing, you would drive more storm surge because you start out with higher water. So the same winds would push a wall of water deeper into land because it starts at a higher baseline. Another factor, number three, that's a very robust projection of a changing climate is that warmer air holds more moisture in vapor form, more water in vapor form, and that means there's more moisture to condense in the form of rain when the conditions are right, as they are in mature hurricanes. So that leads to more intense rain events. And we see that not just in hurricanes, but actually all sorts of rain events across the globe. Number four is something that's gotten a lot of publicity, and that is that, that warmer oceans increase the intensity of hurricanes. There's a pretty strong consensus at this point among the hurricane research community that although the number of hurricanes may not be changing, the fraction that reach the highest intensity levels is increasing and will continue to do so going forward. There's somewhat less consensus about whether that signal is already apparent in the historic record, but there's a strong consensus that if it isn't already apparent, it will be going forward. Number five is a really interesting and active area of research, and that is that changing wind patterns linked to climate change signals might lead to more meandering hurricane tracks, and in fact, changes in other extreme weather patterns. And that's something that Jennifer Francis is an expert on. I'm going to touch on it at the very end of this presentation, and she's going to talk more on it, I believe. And six, I've already alluded to, is that the actual impact of a warmer climate on the total number of tropical cyclones. A tropical cyclone is a generic word for what's called a hurricane in the North Atlantic. The number of those actually is not well known how that will change, and it may actually go down slightly or it may not change much, but I don't want you to glean too much comfort for that, because if you go back to 4 above it, the fraction that reach the highest intensities is what does the most damage, and that's likely to increase. That's my list of impacts. I can't touch on all those in a short presentation, but I'll touch briefly on sea level rise and its impact on storm surge, changing hurricane intensity, and very briefly on meandering hurricane tracks. This is just a brief overview of sea level rise. And as I said, sea level rise is one of the most robust projections of a warming climate. That's simply because warmer seawater takes up more volume, so the level goes up. An increasingly large portion of sea level rise is due to the melting of land-based ice sheets. We've had about 0.2 meters or 20 centimeters of global sea level rise over the industrial era to the current day. And projections going forward are uncertain. They're uncertain mostly because we don't know what we're going to continue to emit into the atmosphere. It depends on what you assume, but also because how rapidly land-based ice sheets break up is a really active area of research, but there's still a lot of uncertainty there. So sort of a plausible range is something between 0.3 and 2.5 meters by 2100. But if you look, so the top left is just the time series of the historical sea level rise going up 30.2 meters over the industrial era, and then the range of possibilities through to 2100 in the colors. But actually, global sea level rise is one thing, but actually sea level varies regionally. So it's not going up at the same rate everywhere. And that's due to things like changing ocean currents, and it's due to factors like local land subsidence. And so you can actually get a factor of 2 variation and on a local basis on the sea level rise compared to the global average. So what I'm showing in the upper right is for Miami now, Miami region, and you see roughly from the present day, the range of possibilities is a little bit higher than the global mean. This is out to 2060. The middle of the road estimate is something around 0.8 meters or 80 centimeters by 2060. What is the impact of that? I mean, if it were just a gradual encroachment, that would be something that you'd have to plan for and allow for, but it might not be catastrophic to coastal communities. But actually, the impact of sea level rise is really felt more catastrophically in the increased frequency of big flood events, surges, for instance. Hurricane winds drive water onto the coast, and if you start at a higher baseline, you drive that water deeper into the coast. And I like to illustrate this point by talking about the city of Tampa. Tampa, it turns out, by a private sector company called Karen Clark and Company, was ranked as the most surge vulnerable city in the US. Why is that? One reason is that the bathymetry, which is the fancy word for the depth of the ocean off of the state of Florida, is very shallow in the Gulf. So as the hurricane, if a hurricane sort of approaches Tampa, it blows water towards the coast, and the coastal waters are very shallow. That means where does that water go? Well, it goes to raising its level in the form of greater surge. Another thing is that Tampa Bay acts sort of like a funnel, that if the hurricane is blowing the water just right, it's going to get trapped in Tampa. It doesn't have anywhere easily to escape. KCC's 2015 report estimated that the 100-year flood, or the flood that can happen with a 1% chance every year, was about a 10-foot surge, a 10-foot elevation of water due to the driving winds of a hurricane above the baseline level. And KCC estimated, based on insurance records and infrastructure and property in harm's way, that would be about a $175 billion insured loss event. One reason to realize how that might be true is that about 50% of Tampa's population resides below 10 feet, below that 100-year surge level. Now, what is the impact of sea level rise on that? That's bad enough, right? But that estimate was based on current sea level. I've tried to illustrate the impact of sea level rise on that estimate with the figure on the right. And the gray and blue curves are calculations of the surge level on Tampa as a function on the y-axis, as a function of how long you have to wait to get that surge level, what we call the return period. So, for instance, at 100 years, or 10 squared years on the x-axis, if you trace that up, you get about 3 meters. So the 100-year event, according to this analysis, is about 3 meters, or roughly 10 feet. So it's consistent with Karen Clark and Company. If you go out to 1,000 years, it's something like 5 meters at Tampa, a little under 5 meters. But that blue curve is according to current sea level. And to first approximation, to get the effects for future sea level, you just shift that curve up by the amount of sea level rise you want to consider. Now, 30 inches of sea level is kind of a middle of the road estimate for something around 2060 on Tampa. So that's the yellow curve I added in there. I shifted it up by 30 inches. And now what was the 100-year return period, or the 1% per year chance at 3 meters, is actually the 30-year return period on the yellow curve. So that by adding 30 inches of sea level, we tripled the chances every year of getting an event of that magnitude. And I want to quibble a little bit with the terminology that's common in this business. We talk about sort of in a blasé way about the 100-year return period. It doesn't mean, of course, that if it just happened last year, you can wait 99 years for the next event of that magnitude. It really means 1% chance per year of it happening. And what I'd like to point out is that so that 1% is switching to 3% with 30 inches of sea level rise, so once every 30 years on average. And the 3% chance means about a 60% chance of an event happening over the lifetime of a 30-year mortgage. So increasing plausible amounts of sea level just a few decades down the road, really have alarming consequences for vulnerable cities like Tampa and other cities. So that's my quick foray into sea level rise and storm surge. The next climate change hurricane impact topic I'd like to address is hurricane intensity. And to talk about this, I need to introduce a concept called potential intensity. It turns out that what determines the intensity, like the circular wind speed, the rotational wind speed of a hurricane, that's one way to measure the intensity, are factors like sea surface temperature, how warm the ocean is underneath the storm, how much moisture is available in the atmosphere, the temperature at the top of the storm in the upper troposphere. These are large-scale climate factors that all conspire to determine what's the maximum intensity, the maximum potential intensity a storm at a location can achieve. It's called the PI, the potential intensity. And this theory, it's a meteorological theory that's well developed. It's based on the fundamental principles of how these meteorological events work. PI is increasing, in large part because the oceans are getting warmer. And that's increasing already. Current trends, the top figure where you see reds and oranges and yellows, that's where it's been increasing over the last several decades. Not everywhere, but in some of the most important hurricanes sustaining ocean basins like the North Atlantic and the Asian Pacific sector. Now, not all hurricanes reach their potential intensity. There's kind of a distribution. Some do, some don't. It depends on the vagary of weather patterns. Like for instance, in 2017, Maria did, but many storms don't. They're kind of like what storms actually do is kind of spread out all the way from almost nothing all the way to the maximum potential intensity that they could achieve. If potential intensity increases, it's like ramping up the speed limit on the highway. Not all cars travel at the speed limit, but if you ramp it up, some are going to hit the speed limit. And if you stretch out that distribution from essentially from 0 up to a higher number at the high end of the distribution, above any given fraction, say category 3, a major storm, you're going to have a higher fraction reaching above that category. And in fact, some storms will hit historical levels never seen. Projections going forward for potential intensity, possibly a 10% increase in potential intensity by the late 21st century, depending on the climate scenario and the region you look at. It varies regionally. One thing to point out is you might think that 10% doesn't sound like that much, but actually what is the damage that wind does on property and infrastructure and populations in harm's way? It's not directly proportional to the wind speed. It's proportional to the cube of the wind speed. So the wind speed times the wind speed times the wind speed. So a 10% increase of wind speed is roughly a 30% increase in the energy that can be destructively dissipated on the shore. And that's why it's the few strongest landfalling hurricanes that have done most of the historical damage. And so really, it doesn't matter that much if the total number of tropical cyclones goes up or down a little bit. What matters more is how many of them reach the most intense categories, because it's the most intense storms that do the vast majority of damage. That's topic 2. I know this is a whirlwind tour, but hopefully there'll be some questions after. The topic 3 is brand new to me, and it has to do with a recent analysis with a colleague of mine about the increasing frequency of hurricane stalling. What do I mean by that? Well, 2 poster children examples are Hurricane Harvey in 2017 and Hurricane Florence in 2018. These storms dumped record amounts of rain on the region, and that's what I'm showing here. Their tracks are the black dots, and then the color maps on the map of the US is proportional to the accumulated rain. And one of the primary reasons these storms were so sort of catastrophic in their rain-driven flooding was that when they hit the coast, they kind of stalled out. They sort of hung out near the coast, right off the coast for long periods of time, 2, 3, 4 days. And that means that there was a long time for the winds over the water to raise up that moist air and then dump it in the form of rain on the coastal regions, Houston or coastal North Carolina. My colleague Jim Costin and I went back and looked at historical records of hurricane tracks since the mid-20th century, and we now see some evidence that there's an increasing trend in storms to stall over all of the North Atlantic and including near the coast. We define stalling by spending at least 48 hours within 200 kilometers of the coast, but you can define it different ways and you get basically the same result. So that figure on the rightmost figure is our plot from 1944 to 2017 of the annual fraction of coastal hurricanes that stall for at least 48 hours near the coast. Harvey and Florence were way into that category. And you can see it's noisy for sure, but there's a distinct upward trend. I have to say, we don't know the exact cause for why this is happening, but we have some suspects. And it may well be related to climate change signals and large-scale wind patterns. And that makes a nice segue into Jennifer Francis's work on this topic. So with that said, I will turn it over to Jennifer, and I'm happy to entertain questions when our talks are done. Thank you.
Thanks, Tim. And now, Dr. Francis, we're going to switch over to your slides.
Okay, thank you. All right, well, hello everyone. Thank you very much for inviting me to be here today, and especially thanks to Tim for that wonderful introduction to how the state of the research is developing with respect to what we know about the connections between climate change and tropical storms. So I'm going to focus on just one of these factors that we think may be having an effect on tropical storms as well. And it may seem extremely counterintuitive to most of you that I'm going to talk about ice and I'm going to talk about tropical storms, in particular, talking about how the Arctic and the fact that it's warming so fast up there, 2 to 3 times faster than the globe as a whole, how that may be influencing the changes that Tim talked about in tropical storms, especially in the Atlantic. But first, let's start talking about the Arctic itself. And in this animation, you're looking down on the North Pole. There's Greenland on the bottom right corner there. And those colors are showing you the thickness of the sea ice that floats on the Arctic Ocean. And the bluish colors are thinner ice. And as we get up to the yellows and oranges, that's thicker ice. And what you notice as this animation goes from roughly 1980, which is only about 40 years ago now, up to the present day in 2019, those orange and yellow colors are disappearing. The sea ice is becoming much, much thinner. And as that ice becomes thin, we're also seeing in combination with that, because of the various feedbacks that happen between the ice and snow and the atmosphere, we are seeing this rapid Arctic warming, which we call Arctic amplification. So what are these possible connections to hurricanes? because of the Arctic warming so fast? Well, one of them that we're very certain about is that because we're losing so much sea ice and so much of the spring snow cover, we've actually darkened the Earth. We've made the Earth as a whole darker than it used to be. And because of that, it means that the Earth is now absorbing more of the sun's energy. This is having an effect on global warming by increasing it by at least 25 to 40%. This is very new research that has analyzed this number. So if it weren't for this snow and ice disappearing on the Earth, global warming would be a lot less than it is. But instead, because we're warming the Arctic so fast, we're getting this uptick in the warming of the Earth. And what does that do? As Tim mentioned, we have more heat in the atmosphere now, we have more heat in the oceans now, and as he said, we also have more moisture in the atmosphere. This is a critical feature of climate change that really doesn't get enough press, in my view, because that moisture does many things. First of all, water vapor in the atmosphere is a greenhouse gas. So it is also increasing the heat trapping effects of global warming, of the greenhouse gases in the atmosphere. That moisture then can condense into clouds, and when that moisture does that, it releases heat into the atmosphere. That heat is fuel for storms, all sorts of storms. And so not only do we have the extra precipitation and the heavier precipitation that Tim mentioned, but we're also adding a lot more energy to the system, and that energy is purely fuel for all sorts of storms, in particular tropical storms. We're also certain that because we're losing the ice that's on land, so this is glaciers, the Greenland ice cap, and also down in Antarctica as well now, we are contributing to the sea level rise that Tim talked about. About half of the sea level rise is due to the loss of land ice. So because the Arctic is warming so fast, it's helping to melt that land ice even faster. And this is contributing to the higher storm surges he talked about. And also, if you're on a coast facing where the storm waves are coming from, those storm waves are going to be riding on a higher ocean, so they're going to do even more damage as sea levels continue to rise. And as Tim also described, we think that there's a direct connection now, and this is becoming increasingly certain, this is still a very hot research topic though, that we think the warming Arctic is also affecting the steering winds, the winds that steer storms. And so I'm going to talk a little bit more about that. So we believe that there are three distinct effects of Arctic amplification, that's what AA is, especially during the summer months. So first of all, we expect to see weakening of these steering winds. The reason for that is because the difference in temperature between the Arctic and areas farther south is one of the main factors that creates the jet stream. It's this fast-moving river of air high over our heads that creates storms and it steers storms. And because the Arctic is warming so fast, that north-south temperature difference is getting smaller, and so there's less force to drive those winds of the jet stream, especially those west to east winds. The third fact is when we see that these winds of the jet stream do weaken, we tend to see the jet stream get wavier. And what I mean by that is it takes bigger swings to the north and bigger dips to the south. And when the jet stream is in one of these very wavy configurations, those big waves in the jet stream tend to stay in one place for a long time. And I'll show you an example in a minute of how it's actually played a role in this past winter and spring's weather events that have been so persistent across our country. The third fact is that there's been a lot of recent research lately that suggests that these very stagnant waves tend to happen mainly in the summertime, also associated with not just weaker winds of the jet stream, but also a tendency for the jet stream to split. So one branch would go to the north and another branch would tend to go to the south. And the storms or the weather patterns between those branches of the jet stream then have basically no wind to push them along, and so they tend to get stuck in place. So these are some of the factors that we think may be contributing to that tendency that Tim just showed you for an increase in the frequency of stalling storms. And I'm just going to show you a little bit of recent work that I've been involved with my colleagues at the University of Wisconsin, in particular, Steve Vavris. So what you're looking at here is a model simulation for the end of the 21st century. And on the y-axis here is the latitude, so going from basically the latitude of, say, South Carolina up to the North Pole. And then across the bottom are two different, this is the metric for waviness of the jet stream, and the blue numbers on top are the speed of the west winds in the jet stream. So what we're looking at is a projection for the month of August. This map here corresponds to the latitude in this graph here. So you can relate these curves to where you live. So the blue curve here is wiggling with latitude. When it is in a negative number, so when the blue numbers are negative here, it means those winds are decreasing in the future. This red curve here is a metric for jet stream waviness. And when those numbers are positive, it means the jet stream is tending to take these bigger north-south swings that I was talking about. So what you notice is that right over the United States, basically the top 2/3 of the United States, the models are projecting that indeed the west winds of the jet stream are weakening or will weaken, and we see this big uptick in the waviness of the jet stream. So as I said, when the jet stream gets very wavy, we tend to see those waves get stuck in one place, and that means the weather systems associated with those waves in the jet stream are also very, very persistent. So this is what I mean by a wavy jet stream. This is a real example from a couple of years ago, just to show you what a typical wavy jet stream looks like. In fact, this particular pattern has been very, very common in the last several years, with this big northward swing in the jet stream over the west coast, which has contributed to the drought that has been happening over the last several years in California. And then we have this southward dip over the middle of the country. So just to show you what a very wavy jet stream looks like. And in fact, when Irma and Sandy came along, two very anomalous storms, we had a very wavy jet stream in place for both of those. And this is what a typical split jet stream might look like. And this, in fact, was only a couple of weeks ago. And it occurred right when we were seeing this very active period with tornadoes up through the middle of the country. When you see the jet in this type of configuration coming from the southwest like this, that tends to bring a lot of energy and moisture into the middle of the country and can spawn very active, severe weather conditions. And this particular example here was pretty much stuck in place for 2 to 3 weeks. We had this split jet. And so as I mentioned, when the jet does tend to split like this, we tend to see the weather patterns associated with it be very persistent as well. And there is new research that suggests that these split jet stream patterns have been happening more often, and they're projected to become more frequent in the future. So some of the, just a couple of examples of some of the very unusual tropical storms we've seen. Hurricane Irene, you might remember back in 2011. This is the East Coast, the Atlantic seaboard of the United States, showing the rain totals that occurred with Hurricane Irene. She did a lot of damage, especially up in New England. She was really not a wind storm. It was really all about the rainfall that she produced. She was a very slow moving storm. Irma down in Florida, in this region here, dumped a whole lot of rain on Florida. And we know, we've already heard about Hurricane Harvey and the fact that when it stalled in place over Houston, dumped some more rain than I think has ever been recorded from a tropical storm. So these were all very unusual storms. And why do we care about understanding what the future holds and what is causing these changes? It's so that we can help planners and decision makers do a better job of preparing their communities for just the type of extreme events that we expect to be on the rise. And that's why focusing on various factors like the changes in the Arctic and the impacts that they may have on tropical storms is such an important area of research. And as I said, understanding what sorts of extremes are likely to happen more often in which regions will help communities get ready for them. And we also have to understand these problems so that we can start thinking about what are we going to do about it. Building more resilient homes, and also thinking about whether we should continue to rebuild homes and businesses and infrastructure in areas that are repeatedly damaged. And this is a tough conversation because oftentimes that means perhaps having to abandon a certain area where perhaps families have lived for generations. So just to wrap up, I just wanted to plug a new paper a new article that I just wrote that came out in this month's issue of Scientific American. If you're interested in this topic, you can read about it here. Thank you.
Great. Thank you so much. It's a lot of important information to take in. Great. So let's open this up to questions. So if you want to ask a question, why don't you click the Q&A button along the bottom of the screen and set that, and we'll set that into motion. And I know there's there's some members of the media on the call, so we would like to take your question first. And if you could, just mention which publication you're with for just to be helpful to everyone who's on the call. My hometown is Tampa, Florida, Dr. Hall. So, and I live on a little barrier island. So there was no good news from you today for me personally. Sorry
about that, Susan.
Yeah. So, and we will be providing a link to this presentation and the slides. So again, you can share it with others or go back and refer to it because it certainly was, meaty. And what do you, one thing that I've noticed just in the last couple days, where the, let's see, I think it was Colorado State University had originally predicted, I guess what they were calling sort of a lighter season, but then they've increased it slightly, and they did, which of course you all reflected in your presentations, that it was the warming of the tropical Atlantic Ocean that's sort of giving that fuel for the formation of hurricanes. So they have sort of upgraded their original forecast. What, Dr. Hall or Dr. Francis, what do you make of that?
I guess I can field that one. Yeah, I mean, the first thing to say is that, as I mentioned in my presentation, seasonal forecasting is a very difficult business. And really the forecasts about, the season coming up when you're a month or two in front of the peak part of the season are only statements about slight shifts in probability for the total number of storms forming over the entire North Atlantic generally. They're not statements, in particular, they're not statements about, whether or not a major hurricane will hit Florida. So the classic sort of qualification of forecasts like that is in Hurricane Andrew, right, in 1993. I mean, that was actually forecast to be a weak season, but it was one of the most devastating landfalls in Florida, Category 5. And then last year was forecast to be an average season, and we had Florence and Michael, another Category 5 landfall. So it's a very difficult problem. I don't want to dismiss its importance. It would be great if we do have a little bit of skill and sort of an overall Atlantic-wide sense of the problem. I'm glad that people are researching it and trying to do better forecasts in that direction. Right now, El Nino we have a mild El Nino, which tends to suppress Atlantic activity on average. But yes, indeed, as you mentioned, we have warmer than average North Atlantic sea surface temperatures, which tends to enhance activity. So those things are sort of roughly canceling each other to lead to, an average or slightly above average season. But again, these are statements about slight shifts in probability. So when I say the season is slightly above average, below average is still a possibility. And so it was way above average. It's just a slight shift in the distribution one way or the other.
Great. Dr. Francis, did you want to add anything to that?
No, I think Tim did a great job. Thanks.
Great. So the next question is from George Siegel. George is a documentary film producer, and most recently the Last House Standing documentary. And he's asking, how realistic is it to get large communities that are prone to damage to relocate, and commenting that you'd have to move most of Florida, I guess, under that definition. So, Dr. Francis, do you want to respond to that?
Sure. See, and I brought that topic up. Excuse me. So, of course, it makes no sense to talk about moving everyone in Florida, but there are areas in Florida that do have some high ground. I mean, if you think back to that image of Tampa Bay that Tim showed, the storm surge, for example, didn't cover the entire half of Florida. There were still places where you could retreat for a while anyway, you know, maybe a generation. But probably in Florida, it makes more sense to talk more about building homes and businesses and infrastructure that's more resilient to expected changes over the next, you know, lifetime of those buildings and infrastructure. But other parts of the country where there is higher ground not too far away, it makes more sense to think about retreating. And even there are some states that are already addressing this in a very active way. I know New Jersey, there are a couple of towns or at least neighborhoods that they are already providing incentives for people who live in areas that have flooded repeatedly and have their homes or businesses destroyed repeatedly, convincing them to move elsewhere. So it's a conversation that's starting to happen. It's not an easy one, but it needs to happen.
Yeah, there's going to be a lot of difficult conversations that we're going to have in the state of Florida and elsewhere around climate. So let me, Reverend Russell Meyer, who is with the Florida Council of Churches, is asking, given that trend projections are historically based and unable to account for the exponential growth in sea level and growing extreme weather variables, what should replace the standard model for policy planning? So, Tim, why don't you start?
Sure. I would first say that that not all climate change projections are historically based. In fact, the basic set of models that are used to project climate going forward are physically based models. They're based on our understanding of, you know, the equations of fluid dynamics and thermodynamics and chemistry. They are validated historically. So we build these models based on our understanding of the physics, and then we have to go back and check to see that they can reproduce the historic record with some fidelity, or in order to have any faith in them. That's true. But that's why, for example, you know, we've had 20 centimeters of global average sea level rise over the industrial era, but we're projecting forward in the next 80 years, possibly a meter sea level rise, 5 times as much as we've already had, because we have an understanding of how ice sheets might melt, perfect, but some understanding. And we have an understanding of, we project the changing composition of the atmosphere due to increasing carbon, fossil fuel, and that causes the sea level to expand. The volume of seawater to expand. So I would say that it's a combination of physically based modeling, but then validated against historical data.
And I
answered one part of the question. I'm not sure.
Go ahead, Tim.
Dr. Francis, you want to chime in there?
So I think this is probably what Tim was going to continue on, but as he mentioned in his presentation, the uncertainties for the future model projections are not so much the understanding of how the system works, and as he said, the thermodynamics and the dynamics. We understand the physics pretty well, but the real uncertainties are coming from what humans are going to do about this. You know, will we be able to curb our emissions of greenhouse gases? Will we be able to reduce the amount of greenhouse gases that are already in the atmosphere, perhaps with new technology being developed that could actually extract carbon dioxide from the atmosphere? So the the biggest uncertainties are really not in the models themselves. It's the information, the assumptions that you have to make about the future that we just can't predict.
Yes. So another question from Pam McVitie out of Tallahassee. Are hurricanes maintaining high wind speeds longer as they move miles inland?
Maybe I should take that one.
Go ahead.
I mean, a hurricane, or more generically, a tropical cyclone, has to be above water to sustain its intensity. Once it moves over land, it really loses its raison d'etre, so to speak. It needs to evaporate warm seawater, and that's really its fuel. So the simple answer is no, you can't propagate an intense hurricane sort of arbitrarily deep over the continent. However, I mean, if hurricane intensity is going up, a stronger hurricane when it hits land will take somewhat longer to attenuate down to, essentially nothing. So a storm that starts at a higher intensity when it makes landfall will last a bit longer over land. But you still eventually you have to attenuate.
And I'd just like to chime in and kind of expand that question a little bit. As the ocean temperatures continue to rise, and we see this occurring particularly along the eastern seaboard of the United States, not so much a question of the wind speeds inland, but what we might expect, and I think there is already some evidence for, we're seeing hurricanes or tropical storms maintain their tropical characteristics at a farther northern latitude because we've got warmer water offshore. And so, as Tim said, they need that warm water to maintain themselves. So if the oceans are warming, there's more evaporation there. So we're seeing storms live longer, basically, as they travel up the East Coast. And by extension, you can also say we're seeing more late season storms, again, because of that warmer ocean. And a couple just recently in October, remember Hurricane Sandy came along basically at Halloween, and Hurricane Michael was also an October storm. So there's some evidence that we're seeing hurricane season lasting longer into the fall.
Great. Dr. Hall, my colleague Chris Carnival had a question about your new research on stalling hurricanes. How much was the increase in incidence of stalling storms over your study period? He was wondering, he thought he saw it correctly, that 4 out of 100 to now 6 out of 100. Is that correct?
It's a noisy signal, but if you draw trend lines to it, which we did, then I can answer your question based on our analysis of the trends. And there's something roughly like a doubling of the chance that a hurricane near the coast will stall for 48 hours or more near the coast over that 74-year period. Another way to say it is that, different ways to say it, we're sort of playing with statistics here, but another way to say it is that we saw over the entire North Atlantic, 66 storms that stalled for 48 hours or more near the U.S. coastline. And of those 66 over a 74-year period, 30 of them happened in the last third, but only 17 in the first third.
Got it. Very good. It's a lot of food for thought on there. So we're getting sort of a last call for questions because we always try to get people out under an hour. Any other further questions? And then I would ask Tim, you and Dr. Francis to just maybe just summarize a little bit for us the end or anything people need to be thinking about as we sort of march down this path, the importance of greenhouse gas reductions as the way so that we do not make these hurricane situations even worse. So as a native Floridian and someone who's been working on climate and energy issues for the last 20 years, it does seem like the hurricanes are one of those canaries in the coal mine that can either get our attention and put us on the right track to adapting to the climate impacts that are already baked into the pipeline, even if we turn the CO2 spigot off tomorrow, and then the real need for dramatic greenhouse gas reductions, so we don't make this problem worse. Just one last thing, Pam McVitie was just asking about the sea level rise projections, and she wondered if they were low, and was the Greenland melt included in that as well?
I guess I showed the slide. I'll take a stab at that, but Jennifer may well want to chime in also. The projections I showed, the upper level projections do include estimates of how much Greenland will melt in the West Antarctic ice sheet. Yes, so they're a sizable. In fact, a majority component of the upper estimates out to 2100. I mean, could it be worse than that? It absolutely could be. I mean, typically you show estimates in some 5 to 95%, probability range to the best of our ability to estimate that range. But that means that there's a possibility of something even further, more extreme. Yeah,
and I'd just add to that I think we are sort of coming at those projections from a conservative starting point. So it seems that the new research that comes out on both Greenland melt and also melt in Antarctica are continually finding that the melting is happening faster than we thought. So most likely those projections are somewhat on the low side, but one of the biggest uncertainties in those projections of sea level rise comes from how fast those ice sheets are going to melt. And that's a very huge area of active research right now. So in the next few decades, or hopefully sooner, we'll have better information to better pin down exactly how fast sea level will rise. But as you can imagine, they're very difficult quantities to really pin down.
Yes, that is where the uncertainty and certainly human behavior will have an impact on that. And just one last sort of clarification from Reverend Meyer, and we can take some of this offline. He's still interested in if there are particular recommendations for what model or models that policymakers should be utilized in their planning, so we can make sure. So why don't Dr. Hall and then Dr. Francis, just if there's anything else that strikes you, or if you have a response to Reverend Meyer, and then after that we'll wrap up. So Dr. Hall?
Yeah, thank you, Reverend Meyer, for your question. And I'm sorry I didn't address it earlier. My recommendation would be to use ensemble models. And what I mean by that is don't rely on any single model, but look at the, the consensus of a range of models as they are collected by international communities like the IPCC. I mean, and statements for policymakers typically don't depend on any single model, but on a group of models, and the group of models that have been validated and considered, reliable to the best of our ability.
Great. And Dr. Francis?
Well, if we're moving into wrap-up mode here, so I would just say that, we've been mostly talking about tropical storms here today, but there are connections between climate change and many other types of extreme weather events as well that are becoming very clear. So the changes that we've already seen in the climate system are already having a discernible impact on the frequency of extreme events, of extreme events, and it's just only going to get more so. This signal that we've been trying to extricate from observations around the world is a difficult one because weather is such a noisy system, but we are able to do that now. There are a lot of people working on this topic, developing new tools to reveal those signals. And as we look forward into the future with ever increasingly accurate models that simulate all these very complicated processes that occur in the climate system, we're also getting a much better, much clearer picture of what the future may hold. And it's not a good picture. We have to realize that we are in for a lot more climate change, even if we could somehow stop producing greenhouse gases today, because every molecule of carbon dioxide, once it gets into the atmosphere, lasts a very long time, and the impacts of that molecule last a long time. So we have to come to grips with the fact that we are going to have to deal with these extreme events, and we're going to have to do our best to prepare for them.
So sobering news. And Dr. Hall, I know you were answering Reverend Meyer's question, so if there was anything you wanted to say just to kind of wrap up.
Yeah, I would just reiterate one of the things that Jennifer said, that we in the business, we talk about warming in the pipeline, and that means that, for example, the oceans are still responding to the greenhouse warming from several decades ago, and even in the extremely unlikely event we were to sort of cap fossil fuel emissions in the next few years, they would go on warming for several decades. So absolutely, we should be looking at alternative energy sources to ultimately cap those fossil fuel emissions. But at the same time, we'll be forced to consider adaptation. And that means a combination, as Jennifer pointed out, of abandoning certain coastal regions that are just not worth protecting, buffering, but also more robust zoning codes in coastal communities. And I will say that Florida, which is ground zero for hurricane hazard in the U.S., has indeed adopted more rigorous zoning codes, and you can see the benefit of that in, say, insured losses. But some of that benefit is overwhelmed by the fact that there are just more and more buildings going up. So you have more robust buildings, yeah, but even more buildings overall. So it's a complicated thing, but there's going to be just as much adaptation as there is going to be mitigation for decades to come.
Yes, we're going to have to do all of that. So very good. That has just been incredibly insightful to me as well. So I want to thank everyone. Obviously, Dr. Hall, Dr. Francis, so appreciate your sharing your research and all your findings, and everyone who's on the phone for joining us today and all the thoughtful questions. Today's presentation has been recorded, and we will send you a link to that recording once it's been processed. And if you found today's presentation useful, I do hope you'll consider joining the Southern Alliance for Clean Energy so we can continue to work towards those clean energy solutions that we were hearing about that are so necessary. You can visit us at cleanenergy.org. So take care, everyone, and have a great week, and appreciate your time.
Thank you.
Thank you.
Thank you.